keep running now. Yeah, so it looks like it is T4 because if for F intersect F prime to be empty, we must have one of them to be empty, right? So let's just say F is empty. So T4, should I write the definition? It's very similar. Don't need to erase the whole thing. So T4, if F and F prime are closed and disjoint, then there exist open sets U and V such that all of that is true. Well, in order to create this, right, we must have one of the sets empty. Let's just say without loss of generality, F is empty. Okay, so then I can choose the set U to be the empty set. And certainly F will be contained in that. Okay, and then I need an open set. I need an open set containing F prime.
It would be
It would have to be. It would have to be all of. Well, it could be actually any. It has to be just any one of these closed. It can be any closed set, basically.
I thought we were supposed to be open. Yeah.
U has to be. I'm saying, but the F prime.
Right.
Sorry.
So the only open set containing F prime has to be X.
Because
Yeah.
it has to be contained.
Because F prime will contain pi.
Right?
Well, okay. I guess these both could be empty, is what I was thinking. The F and the F prime could both be empty, and then in that case.
Oh, yeah.
In that case, U and V could both be the empty set. But you're right. So as long as F prime is not empty, then it has to contain pi, and so then you have to choose V equal to X, which we can do anyway because it'll intersect with U trivially. So, okay. So it is T4. So this one is T4 and T0, but it's nothing else. So it's a little bit tricky, but I actually like these kind of problems because it's like, it's a topology. I mean, you should expect on the test, I'm probably going to give you a question where there's a topology that you've never seen before. I'll give you something just to really get you to think about it, rather than, it's not like every problem is just going to be the real numbers with the absolute value metric, because that's almost like Math 350, right? So I want to have you play with the more abstract ideas that we have here. Okay, let me give you some more questions about this same topology. I like this example. You guys doing okay?
Yeah.
Okay, great. Okay, let's talk about a follow-up here. Is X comma tau compact? I haven't done much with this yet, so I want to start thinking about the 7.1 stuff. Is this a compact space? So let's just remember, a compact set is one where every open cover has a finite subcover. Okay? So the question is, does every open cover of X have a finite subcover? And by finite subcover, we just mean a finite number of sets covering it. Okay? Obviously, the set of real numbers is infinite. That's not the point. The point is, if we take any open cover of X, can we reduce that cover to only finitely many sets that are doing the covering? Okay, so let's think about open covers of the real numbers. We're trying to cover all real numbers only with open sets. We can only use the open sets right now. So, here they are. What can you tell me about an open cover of the? Is there anything you'd be able to say if you expect to have an open cover of the real numbers? using these open sets, can you tell me anything about what has to be in that open cover?
X would have to be in the open cover because no matter what we pick, we'd be missing a point of X.
You've got to cover all real numbers, including pi, right? None of these open sets are going to cover pi. So any open this is the key point. Any open cover of X in this topology, any open cover of X must have X in it. Okay, let's write that down. So note that every open cover of X must include X in it. Okay? So then the question is, will there be a finite subcover? Just the X by itself. Right, exactly. Remember, I'm just saying when I say a finite subcover, I don't mean the set itself is finite. I just mean the number of sets that you are using to cover the space is only a finite number. Guys, if X is in your open cover, then you can cover X with just one set, namely X itself. This one is available to you. You just use that to cover the whole real number line. So therefore the answer is yes, this is compact. So such a cover has a finite subcover consisting of just the set X alone.